Welcome back, guys. Today we're going to be looking at topic 6.5, which is solving exponential equations. Now, over the next few lessons, we are going to be doing solving a variety of equations. Today we're going to be specifically looking at equations where we have a rational exponent or where we can write our equation with the same base. So let's get started. First of all, we're going to start with rational exponents. Now, if something is written with a rational exponent, a rational number is anything that can be written as a fraction. So we could have x to the 1/3, we could have x to the 1/2. We can also have x cubed because x cubed is the same as x to the 3/1. So if our exponent is written as a fraction or as a rational number, we have a way that we can solve that. Notice that our base is the unknown. So if we have to solve an equation where we have a rational exponent, the first thing we're going to do is raise both sides to the reciprocal power. And the reason that we're doing that is because by raising it to the reciprocal power, we ultimately cancel out that exponent and leave it as x to the 1. So for example, if I had x to the 1/2 and I wanted to solve for x or have it just say x to the 1, I would multiply or raise it to the power 2/1, which based on my exponent laws, I would multiply, and 1/2 times 2/1 would just give me x to the 1. So that's the purpose for raising it to the reciprocal power. So again, we want to make it so that our exponent is 1. Now, after that, we would just simplify and solve for our variable. So we're going to start off by looking at an example here where we're going to take a look at how we would have solved this question in, say, grade 10 and how we can solve it now with some of these skills in grade 12. So the volume of a beach ball is 50,965 centimeters cubed. We're asked to determine the radius of the ball to the nearest tenth of a centimeter. And just as a refresher, the formula for volume of a sphere is 4/3 pi r cubed. So we would have had a question like this in grade 10. We would have taken the formula V equals 4/3 pi r cubed. We would have subbed in the value for V, so volume is 50,965, set it equal to 4/3 pi r cubed. From here, though, we need to solve for the r. So our first step would be to divide by the 4/3, or another way to look at that is to multiply by 3 and then divide everything by 4 pi. So ultimately we're left with 3 times 50,965 divided by 4 pi, that's all one exact number, equals to r cubed. So if I had, for example, a simpler version, we had 12 equals r cubed, and I wanted to get r by itself, I would typically cube root. And so one way to solve this is to just cube root both sides. So if I have r cubed equals 3 times 50,965 divided by 4 pi, I could just cube root both sides. Now this one's a fairly messy number, but we would just enter it in our calculator by using some brackets. So if I wanted to put this in my calculator, first of all, I'm going to go to the math function, choose cube root, and I'm going to have 3 bracket 50,965 divided by bracket 4 pi. And we hit enter, and we get 22 point repeating 9. So we have 23.0 centimeters. So this is the way that we would have solved it in grade 10, and it's still a valid way to solve here. So anytime we have a squared or a cubed or a exponent to the fourth, we can certainly solve by taking the cube root or the square root or the fourth root. But particularly when we get into fractional exponents, where we have like a 1/2 and a 1 cubed, there isn't a way to do it that way on our calculator. So another way that we could solve this problem is by raising our exponent to the reciprocal exponent. And the reciprocal of 3 is 1/3. So we're going to raise both sides of this equation to 1/3. So on this side we have 3 times 50,965 all divided by 4 pi. And we're going to raise both sides to the exponent 1/3. So again, putting this in our calculator, we would have, I'm going to actually type in the number first and then do the 1/3 after. So we've got 3 times 50,965 divided by 4 pi equals that number. Now we want to raise that to the exponent of 1/3. So exponent bracket 1 divided by 3. In the newer calculators, it automatically raises your exponent into exponent land. And we get 22 and repeating 9. So 22.999 gives us 23.0 centimeters. So again, if our exponent, our rational exponent, is just a number over 1, we can still use this method of taking the nth root. But again, once we have fractional exponents, then we have to start looking at it a little bit differently. So our first example here, we have x to the 1/2 equals 12. Well, our goal is to get x by itself, meaning we need it to be x to the 1. And so the way that we're going to do that is to raise our power to the reciprocal exponent. So I have x to the 1/2 equals 12. And to get x to just be x to the 1, we're going to raise this to the reciprocal power of 2. And so that's going to leave us with x equals 144. For our next question, we are going to divide by 2 to get x isolated. That's going to leave us with x to the 1/3 equals -1/2. And we'll have to raise this to the reciprocal power. Well, the reciprocal of 1/3 is 3. And so that's going to leave us with x equals -1/8. Now for our final example here, we're going to divide by 3. And that gives me x to the -2/3 equals 9. And again, we need to get rid of our exponent. So we're going to raise it to the reciprocal power. But if you notice, we have a negative here. So that means when we have to raise it to a negative reciprocal, so that the negative and the negative make a positive. So we're raising it to the reciprocal -3/2. Or we're raising it to the exponent -3/2. So that leaves me with x equaling 9 to the exponent -3/2. So on our calculators, we have 9 exponent -3/2 gives us 1/27. All right, so again, when we're working with rational equation or rational exponents, the way that we eliminate that exponent is to raise it to the reciprocal power. All right, so the other thing that we're going to look at solving today is solving equations with a common base. So exponential equations with a common base. So first of all, just as a refresher, an exponential equation is any equation where the variable is in the exponent. So we have, as an example here, 3 to the x is 27, 2 to the x plus 3 is 32, 4 to the x is 2. So to be exponential, the exponent or the variable has to be in the exponent position, or as I've said before, in exponent land. Now, many exponential equations can be solved simply by writing our left side and right side using the same base. And so we're going to go through some practice of how to write things in the same base. So as an example, 81 to the x can be expressed as base 3. That means we're ultimately rewriting 81 as 3 to some exponent. And so sometimes there's a little bit of guess and check involved here. For example, I might plug in 3 cubed and get 27. Well, I know I have to go higher than that. So 3 exponent 4 is 81. So 81 written as base 3 is 3 to the 4. And so if I had 81 to the x and I wanted to write it as base 3, I'd start off by writing 3 to the 4th, and then I still have the x there using my exponent laws, 3 to the 4x. Now, as a refresher here, I've made a list of all the perfect squares up to 16 squared and all the perfect cubes up to 6 cubed. Now, for your lessons here, you have these notes in front of you, but typically if you want to be quick to do these, memorizing your perfect squares up to at least 15 squared and your perfect cubes up to at least 6 cubed is usually helpful, because those are the most common ones that you're going to come across. All right, so we're going to take a look at some examples here. All of these are just practice writing numbers as a separate base. So the first question says to write 9 to the 4x as base 3. So we're really just trying to rewrite our 9 as base 3. And so looking at our chart here, 9 is 3 squared. So 3 squared to the 4x equals 3 to the 8x. The next question is 625 to the exponent 2 minus x, and we want to write that as base 5. So this one here has a little bit of guess and check involved. On your calculator, you would play with your numbers and you'd find out that 5 to the 4th equals 625. So we're just rewriting that 625 as an exponent with base 5, or sorry, as a power with base 5. So we've got 5 to the 4th and then raised the exponent 2 minus x. So multiplying that out, we have 5 to the 8 minus 4x. Next question is 4 times 8 to the x. We want base 2. So we're going to write the 4 as base 2 and the 8 to the x as base 2. We can't actually multiply these numbers yet because we can't combine powers that have different bases. But if we write everything as base 2, we'll be able to combine some things afterwards. So 4 can be written as 2 squared, and 8 can be written as 2 cubed, and 2 cubed to the x becomes 2 squared times 2 to the 3x. Now we have the same base, so we can rewrite this as 2 to the 2 plus 3x. All right, moving on, we've got 1 over 512 to the 5x, and we want to write this as base 2. So we'll start off by writing the base 2 in the denominator. So 512 is the same as 2 to the 5. So we're going to have 2 to the 5, and we've got, actually, let's double check that. So 2 to the 5, no, let's try 2 to the 9, I believe. 2 to the 9, there we go. So this can be written as 2 to the 9, and then to the 5x. So that becomes 1 over 2 to the 45x. But we want to write this as base 2, not 1 over base 2. So we're going to rewrite this as 2 to the negative 45x. All right, now these get a little trickier when we have the fractions, but if it's written as base 2 over 3, that's fairly helpful because 16 can be written as base 2 and 81 can be written as base 3. So 16 as base 2 is 2 to the 4th. 81 as base 3 is 3 to the 4th, and then that's all to the exponent x plus 3. So rewriting that, that's the same as going 2 cubed to the 4th, and then raised to the power x plus 3. And rewriting this again, we would have 2 cubed to the exponent 4x plus 12. Now the challenge comes in if I have the reciprocal base. So if I have 16 over 81 as base 2 over 3, or sorry, 3 over 2. So notice the only difference here is our base has been flipped, which ultimately means all that we're doing is making our exponent negative. So to do a question like this, we're going to start off with what we already know. 16 over 81 can be written as 2 cubed to the 4th, and then that would be to the exponent x plus 3. But we want our base to be the reciprocal of this. So if we make it the reciprocal 3 over 2, that means that our exponent has to become negative. And so we write everything out and then we simplify. So 3 over 2 to the negative 4x minus 12. All right, so let's look at some examples that specifically relate to solving equations. So if I want to solve exponential equations, the first thing I'm going to do is to write each side of the equation in the same base. Now there are going to be questions coming up in future lessons where we can't write using the same base, and that's when we're going to get into logarithms. But right now, all of the questions that you're going to see in this lesson can be written with the same base. If necessary, use your exponent law so that each side of the equation contains only one base. So sometimes you might have to combine values or combine powers. You want to set the exponents on each side of the equation to equal each other, so equating the exponents. And then you're going to determine the value of the variable. Once our bases are the same, for example, if I had 3 to the x equals 3 squared, once our bases are the same, if I have the same powers and the same bases, I have to have the same exponents. So if my powers are equal, my bases are the same, then I know my exponents are the same. So the purpose of getting everything written in the same base is so that we can equate our exponents. All right, so let's take a look at the first example here. We have 8 to the power 2x plus 3 equals 8 to the 7. These are powers that are equal to each other. They already have the same base, so then we know that the exponents are the same. So those first two steps are ultimately skipped because that work's been done for us. So we have 2x plus 3 equals 7. Subtracting 3 from both sides gives me 2x equals 4. Dividing by 2 gives me x equals 2. Now we can check these on our calculator graphically. On our calculator, I could graph 8 to the exponent in brackets 2x plus 3. And I can graph 8 to the 7. And I could see how these intersect. And second calc 5, enter, enter, enter. And we would get x equals 2. So we can solve these on our calculator simply by putting y1 and y2. And so we'll look at that again later on. So for the next one here, we have 7 to the x minus 4 equals 343. We have equal powers, but they don't have the same base. So our first goal is to write these in the same base. And so 7 is the smallest I can go there. So I'm going to do a little guess and check with the 343. So I'm going to start by guessing 7 exponent 3. And that happens to be the right answer. I knew that 7 squared was 49, so my next guess was to go 7 cubed. So 7 cubed is 343. So we write this as 7 to the x minus 4 equals 7 cubed. So we haven't changed anything other than rewriting that as a new base. Our powers are equal, our bases are the same, so we now have x minus 4 equals 3. So x equals 3 plus 4, which is 7. Again, you can double check this by doing left side, right side, or by verifying with your calculator. Next question, we have 3 to the exponent 5 minus 1 and 81 to the exponent 3x. So we're going to write both as base 3. So 3 to the 5x minus 1. And then again, guessing and checking with the 81. 3 cubed is 27. So we try 3 to the 4th. 3 to the 4th is 81. So we rewrite 81 as 3 to the 4th, and then remember there's still the 3x outside. So simplifying, we have 3 to the 5x minus 1 equals 3 to the 12x. Once our bases are the same and our powers are equal, then we can set our exponents equal to each other. So 5x minus 1 equals 12x. Subtracting 5x from both sides gives me negative 1 equals 7x. And that gives me x equals negative 1/7. All right, last one gets a little bit trickier because we're going to have to do some combining with exponent laws, but our first step is to write everything as base 2. So we have 2 to the x, we're going to leave that as 2 to the x, equals 8 root 2. Well, 8 as base 2 is 2 cubed, and root 2, if you remember, root 2 is the same as x to the 1/2. So if I had x to the the nth root of x to the m, that becomes x to the m over n. If you remember, we've got a little 2 right in there and a little 1 here. So this becomes 2 to the 1/2. And then using our exponent laws, when we're multiplying powers to the same base, we add our exponents. So 3 plus 1/2 is 3.5, which is 7 over 2. Once we have equal powers and the same bases, then we can equate our exponents. So we have x equals 7 over 2. Once we're able to solve these equations, then we can get into some word problems. So example number 5 says that a bacterium triples every 6 days. The number of the bacteria N present after X days is given by this formula. So N equals 3 to the X over 6. The question is, after how many days are there 243 bacteria? Well, the 243 represents N, so we have 243 equals 3 to the X over 6. So to solve this question, we're going to have to rewrite 243 as base 3. So 3 exponent 4 is 81, so let's try 3 exponent 5. 3 exponent 5 is 243. So 3 to the 5th equals 3 to the x over 6. Again, powers are equal. Exponents then can be set equal to each other because the bases are the same. So 5 equals x over 6. Multiplying by 6 on both sides gives us 30. So x equals 30, and it's 30 days because that's our units. All right, taking a look at one more example here. So it says to consider the exponential equation 27 to the x minus 2 equals 1 over 81 to the x plus 3. We're actually going to start by solving with method 2, and then we'll go to the calculator. So for this example here, we have 27 and 81. I can't write 81 as base 27, so I have to think, how can I write 27 as bases? And if I start thinking back to my cube roots and my square roots, I know that I can write 27 as base 3. And then when I start looking forward, I can also write 81 as base 3. So 27 is 3 cubed, so I can write this as 3 cubed to the x minus 2. And then 81 to the x minus, or x plus 3, 1 over 81 to the x plus 3 is the same as 81 to the negative 1, and then x plus 3. So we can rewrite this as a new exponent here. So 81 is the same as saying 3 to the 4th. So I'm going to rewrite it as 3 to the negative 4, and then outside I've got x plus 3. So multiplying everything out, I'm going to have 3 to the 3x minus 6 equals 3 to the negative 4x minus 12. Once again, I have the same, or I have equal powers, I have the same bases, meaning I have the same exponents. So simplifying here, I have 3x plus 4x, so 7x. And then I'm adding 6 to both sides. Negative 12 plus 6 is negative 6. Dividing by 7, I have x equals negative 6 over 7. All right, so let's see how we would check this on our calculator. So this particular question is a little bit more complex, so we're going to have to use some brackets. But we'll start off with the first piece here, 27 to the x minus 2. Again, if you have a newer calculator, you won't need the brackets as much. But we've got 27 exponent x minus 2. And then for the second equation, we have 1 divided by, in brackets, 81 exponent bracket x plus 3. And we'll close our brackets. Now, when we graph the functions here, it's not gonna look like these are really intersecting, but that's because these are exponential functions and they're getting closer and closer and closer to 0 without touching. So if I go second calc 5, enter, 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 I get an intersection point of negative 0.857. And if you put negative 6/7 in your calculator, you'll see that they're the same decimal. Now, if I wanted to zoom in a little bit, I could use zoom box. But as close as these values are getting, if you notice when we intersected, the y value was pretty much 0, really close to 0, but not actually touching 0. But that would tell us that we're probably not going to see much different when we zoom in, because the pixelation on our calculators won't let us go much smaller than that. So again, it doesn't look like the graphs are intersecting, but if I do my calculation here, second calc intersect, you'll notice that there still is an intersection point. And again, it happens at negative 0.857. Now, if you have a newer calculator, and it doesn't work with all TI-84s, but it does with most, after you've done this intersection point, you can actually go second function answer, and then type math frac. Now, my calculator will not change my answer, but on some of the newer calculators, when you do that, it will actually convert that decimal to a fraction for you. Again, mine is an older calculator. It doesn't have that methodology or ability to do that. But again, putting this in our calculator, we had y1 as 27 to the x minus 2. We had y2 was equal to 1 over 81 to the x plus 3. And we intersected at x equals negative 0.86, which we actually, using the newer calculators, can find out to be exactly negative 6 over 7. All right, so that's the lesson for today. Make sure that you try a few practice questions. We're going to be continuing to solve equations in the next few lessons, but ultimately our starting point is always to write our equations in the same base. That's the quickest and easiest way to solve whenever we can. Going forward, we're going to look at some examples where we can't just write everything as the same base. All right, have a great day, guys. We'll see you soon.